This week, we begin the discussion of Euclid's Elements, the first mathematical treatise that laid foundations for the mathematical logic and the way that we prove things in the modern mathematics. First, let's talk about the man himself, Euclid. We actually know very little about him. We know that he lived in Alexandria around 300 BC, and we know that he studied in Plato's academy. And that's about all we know of Euclid. We do have quite a few of his works saved through, not in original sources, but through commentaries and copies, the Elements being the main one, but also several of his either minor works. The optics, the data, and the phenomena have been preserved. For any of the treatises, Euclid didn't actually say why he wrote them and how he composed them together, but given that he was a student of Plato, we can conclude that he considered his work to be valuable because of the sheer knowledge that it contained, the intellect that could appeal to those who could understand the actual work. So what about the Elements themselves? First, it's important to understand that Euclid isn't the main author of the Elements, rather he is the editor-in-chief, if you wish, and the Elements themselves are organizations of separate discoveries that have been known by the time of Euclid. Eudoxus, Pythagoras and the Pythagoreans, Hippocrates, and a lot of other Greek mathematicians. What Euclid did, his biggest contribution to ancient and modern mathematics, is the choices of the axioms, the organization, the sort of pyramid-like way to organize mathematical proofs, and the rigor of them. That is all Euclid's own, and that is what we owe to him in terms of mathematical development in this Greek vein. We do not have a single original copy of the Elements. What we have are a variety of commentaries and copies. Most extensive commentary is by Proclus, and you notice that this commentary comes almost 700 years after Euclid actually lived. So Proclus is likely not commenting on the original source either, but rather on the copies of it. Theon of Alexandria's edition of the Elements has been used as a book, and this source is essentially the one that every other copies stem from. Recently, well, somewhat recently, in terms of the history, in the 10th century, there was a manuscript found in Vatican that was not derived from Theon's, and that has been used to sort of compare and figure out new information that the original copy of the Elements might have had versus what has been added by later editors. And there's also a number of various Arabic translation and commentaries that have proven invaluable in figuring out what was Euclid's own and what came in the later centuries. Overall, the Elements both summarize mathematical developments of the age and set up logical development of the subject going forward. So it's really no surprise that it was actually among the very first published books. Its first edition appeared in 1482, and it's been estimated to be second only to the Bible in the number of editions published since then. For centuries, quadrivium, part of which was geometry, was considered to be part of the absolutely necessary education of anybody who would call themselves an educated person. And it was not only until the 20th century, by which point in time Euclid's Elements have actually penetrated materials like textbooks and other school resources thoroughly, did the book itself stop being considered something that everybody who has had higher education has had to actually read. So what does this book look like? What does it contain? Altogether, we have 13 books and 2 that were added by later writers. Book 1 is what we can generally call the toolkit. It goes through the properties of rectilinear figures and circles. We move into Book 2, which is geometric algebra. Book 3 and 4 really dive into circles. Book 5 talks about proportions. Book 6, similar figures. Books 7, 8, and 9 are basically foundations of the number theory. Book 10 is incommensurables, and then the later books talk about solid geometry and the method of exhaustion, which is really at the roots of calculus. What makes every book and the overall structure so special is the actual organization of it. Each book contains numerous propositions organized in a logical sequence, building on top of each other like a pyramid leading to the top result or results, every subsequent proposition relies on the previous ones. So let's take a look at book 1 as an example of that. It starts off with 23 definitions, some of which are arguably added after Euclid. It also starts off with 5 postulates and 5 common notions. So let's take a look at the definitions first. Definition 1. A point is that which has no part. We can understand that at the very base, we have to define some things without much content to work off of. So some of the beginning definitions are going to be fairly vague. A point is that which has no part. A line is a breadthless length. It's important to notice here that the way that Euclid defines a line doesn't mean it's straight. It's a breadthless length. It can be a curvy line, just like this. The ends of a line are points. So if I draw a finite line, that at the very end of it are 2 points, each of which has no part. As we go through the various definitions, and I encourage you to look them up, we encounter some that are a little bit more wordy and substantial than others. And it really is a great exercise in translations from the sort of ancient Greek to the modern rhetoric that you should follow through just to see how language of mathematics has actually developed through the time. There are some definitions that, as I already mentioned, are arguably added by later writers. And for example, here we see in definition 22 the definitions of a variety of quadrilateral figures, a square, an oblong, a rhombus, a rhomboid, and so on. What is interesting, though, is that Euclid only ever uses square. And given how minimalistic he is in his approach, it is unlikely that he would have provided definitions for the other figures that he does not use. He only uses a square. All the other quadrilateral figures are parallelograms to him. Now, once we get through the definitions, the next part of the first book are common notions. Common notions are universal axioms applicable to all sciences. So these are principles that will work across all sciences and not disciplines such as mathematics specific. Things that are equal to the same things are also equal to one another. We have modern words for that, so this is something like the transitivity property. If equals are added to equals, then the wholes are equal. If equals are subtracted from equals, then the differences are equal. Things that coincide with one another are equal to one another. This is an important thing for him, as we will see in some of the propositions, because Euclid takes a more physical approach to some of his constructions. The whole is greater than the part. True in mathematics and outside of it. That's what makes up the common notions. Next up are the postulates. The postulates, different Greek philosophers actually consider them differently, but the postulates are basically more discipline-specific axioms. Aristotle says that postulates need not actually be true, but will later be tested against reality. Once you develop your theory, you test it in the real world, and you see if your postulates are true. Proclus says all math is hypothetical, so you might as well decide on your postulates and work up from there. We will take all the common notions and the postulates to be true, but let's see what the postulates actually say. The postulates postulate that it is possible to do these different things. It is possible to draw a straight line from any point to any point. That means that when we're constructing things, we can assume that given 2 points, I'm always going to be able to draw a straight line. It is also possible to produce a finite straight line continuously in a straight line. So I can start with a straight line between the 2 points constructed by the postulate 1, and I'm able to produce it continuously in a straight line. I am also able to describe a circle with any center and any radius. So you have yourself an actual working compass. Postulate number 4 says all right angles are equal to one another. This one is a little bit interesting, right? How can that be not true? And why is it always true for right angles? Why doesn't it say that all 30-degree angles are all equal to one another? Why just right angles? And one of the hypotheses here is that this is a way of Euclid to be sure that we're actually working on a plane. If you think of, for example, a cone, like an ice cream cone, the cone point at the very top of this three-dimensional surface is not where two right angles are going to actually be equal to one another. So to avoid maybe this type of corners, Euclid postulates that right angles are all equal to one another. And then postulate number 5, of course, the most content-rich postulate, says that if a straight line falling on two straight lines makes the interior angles on the same side less than two right angles, the two straight lines, if produced indefinitely, meet on that side on which the angles are less than two right angles. I encourage you to pause for a second here and try to draw this for yourself. So let's see what we actually got here. Hopefully my picture looks similar to yours. If a straight line falling on two straight lines means that I have to start with two straight lines in the most sort of general position and a third line falling on top of them. Okay? If it makes the interior angles on the same side, so with respect to this line that falls on top of the other two, it of course has two sides, let's say the left side and the right side here. So if the interior angles, these guys, on the same side, either left or right, are less than two right angles, so let's see, is that the case here? If I add these two together, will they be less than two right angles or more? Well, thinking for a second, you'll notice that this will be more because, well, this is greater than 90 degrees, this is greater than 90 degrees, but these two guys together will be less than two right angles. So this is the side I'm interested in, this direction right here. Then what happens? Then the two straight lines, the two original straight lines, if produced indefinitely, meet on that side on which the angles are less than two right angles. So what that says is if I produce these indefinitely, I will find myself a point of intersection. Postulate number 5 is also what is called the parallel postulate, although it sort of talks about something exactly not parallel, lines that do end up meeting. There are a number of equivalent statements that have been proven to be equivalent to this parallel postulate. One of the most useful and popular ones is called Playfair's axiom, named after the Scottish mathematician John Playfair. And it states that in a plane, if you have yourself a line and a point not on that line, then there is at most one line parallel to the given line through the point that you chose. For centuries, really, for 2,000 years, there have been numerous attempts made by mathematicians to not have to include postulate number 5, to be able to prove it from the first 4. The first 4 postulates are nice and what we would consider self-evident, whereas the 5th one is something that feels like it can come from the postulated axioms. Now, unfortunately, all of the attempts have actually failed, or rather, really, quite fortunately, because it appears that this parallel postulate lies at the heart of Euclidean geometry, and changing it produces geometries that are different, geometries that have different actual rules and different propositions and different results. One of the earliest ones, for example, is the attempts by Omar Khayyam, a famous Persian mathematician and poet, to disprove or prove this postulate that ended up in some of the earliest results belonging to what we now know as elliptical and hyperbolic geometry. So, a quick rundown as to what the postulates give us. To be able to draw a straight line means we have a straight edge. Notice that we have a straight edge, but no measure marks on it, so we can't measure distances. We're able to draw circles with a compass, but Euclid assumes the most basic compass, so the one with 2 legs, one of which he fixes at the center of what is to be the circle, and the width of it is said to be the desired radius, and then he traces the circle around. However, he assumes the compass is so-called collapsible, which means that the moment I pick it off the paper, it folds down into 2 legs on top of each other. So the compass cannot be used to move distances either. And then we're going to see what these 2 simplest tools can actually give us. Let's take a look at the first few propositions. The very first proposition is setting off a goal to construct an equilateral triangle on a given finite straight line. So I have myself a finite straight line, a line segment, and I would like to construct an equilateral triangle on it. Try to do it with just a straight edge. it will provide to be a frustrating and impossible task. So a compass is necessary. But how do we use it? Pause the video and try it. I do this with grades 8 and 9s in my math camps, and this is really a fun activity that will yield some unexpected results fairly quickly. So the first thing to do is to try out a bunch of different things. And this construction is fairly simple, that the first couple of steps will probably suggest a right approach. You first place your compass on the left point and make the radius the length of the line segment. So you draw yourself a circle this way. And then we're going to flip sides. I'm going to place my compass on the other point, set my radius to be the same as before, the width of my line segment, and draw myself a second circle. The points of intersection actually produce two equilateral triangles, just like this. Pick whichever one you like best, and here we go. Isn't this great? Such simple tools and such an amazing result right away. This is our first construction. The second Euclidean construction is actually an exercise in moving measurements. So this is saying to place a straight line equal to a given straight line at a given point somewhere else. So I want to move this distance over to here by constructing a line segment of equal length. This basically will give us a rigid compass, a compass that can move distances. So notice that Euclid prefers not to make a stronger assumption that he has a compass that can move distances, but rather start with a collapsible compass and then prove that a collapsible compass can now move distances. After proposition 2, for the rest of the elements, he can now assume that his compass is rigid and can move distances. Let's see how this construction and this proposition actually works. So, to place a straight line equal to a given straight line with one end at the given point. I'm going to use GeoGebra Calculator Suite. You can access it through the browser or through the app. The browser actually has more built-in features, so I'm going to use that. Notice the first thing when I open the tools is there are a lot of different tools. We're going to restrict ourselves to straight edge and compass. Also notice that by default, the software gives me a grid, coordinate system. Well, Euclid of course didn't have a coordinate system, so I'm going to get rid of all of that. And here we are, starting like Euclid did, with a blank sheet of paper or papyrus. So remember, we're starting with a point. So let's place a point. There we go, point A. GeoGebra will automatically label all the things for you. And we start with a line segment, B, C, somewhere like this. Okay? The first step in the Euclidean construction, as he lays it out in the elements, is to construct an equilateral triangle, DAB. So I have the points A and B. I'm going to construct an equilateral triangle on that. And I'm actually going to follow through the construction that I already talked about. I'm going to place a compass at A and draw a circle of radius AB. I'm going to then place my compass on B and draw a circle through A. Here are two of my circles, and I know that the points of their intersection is going to create my equilateral triangle. Now, because now I have quite a bit of circles in my construction and it's going to probably obstruct the view, I'm actually going to go ahead and hide them, okay? So I'm going to pick all the things I do not want and actually hide them from view. I'm then going to connect the points AD and AB and DB with lines to see my little equilateral triangle. All right, so what do we do next? According to Euclid, the next thing to do is to extend DA and DB. So this is where I can use the ray to extend things out. Okay, again, notice that GeoGebra actually labels all of my lines and line segments, and I'm going to let those labels be for a second. Next step in Euclidean construction is to construct a circle centered at B with radius BC. So centered at B with radius BC. I'm going to label the point of intersection of that circle with the extension of the line DB. And then final step in my construction is to construct a circle centered at D with the radius DE. There it is. I'm going to label my point of intersection of this big circle with DA, and I'm done with my construction. The claim is that AF is equal to BC. Let's see how we can prove that. So here's my construction, the picture I ended up with, and here are the steps that we took. The claim at the end is that the line segment AF is actually equal to the line segment BC. Let's record that. This is what I think I've managed to construct. The claim is that AF is equal to BC. So the construction has succeeded. I have managed to place a straight line equal to the line segment BC with one end at the given point A. Now, how do I go about proving it? Well, it's all about using what I've constructed. So let's notice some of the things that are equal in the picture. There's a number of things I can do, and I can do them in different order. Let's say I first notice that BC is actually equal to BE, because of course, remember that I've constructed this circle by placing my compass at the center B, and I know, of course, that every point on the circle is equidistant from the center. So my first observation is that BC is actually equal to BE. What else can I observe? I can also observe that, for example, DA is equal, of course, to DB because I've constructed that as an equilateral triangle. Let me record that. That will likely become useful. And then finally, I can also notice that DF is equal to DE because, again, I've constructed a circle with center at D, and every point on the circle is equidistant from its center, including F and E. So DF is equal to DE. And now I'm going to use the axioms and the common notions and the previous constructions to prove that this yields that AF is equal to BC. So what do we have? I can notice that because of these two, let's take a look at the picture again. DF is equal to DE, and also DA is equal to DB. Common notion number 3 claims that if I take equals from equals, I end up with equals, which will mean that my AF is equal to BE. Okay, so these two, by common notion 3, result in the fact that AF is equal to BE. And now I can put this fact together with this fact. AF is equal to BE and BC is equal to BE. Remember common notion 1, transitive property? If two things are equal to the same, then they're equal to each other. So from these two facts, and by common notion 1, I can deduce that AF is in fact equal to BC. That's Euclidean proof. It is so elegant and so beautiful because we end up using every piece of information that came before this particular proposition. We use proposition 1 to construct an equilateral triangle, and then we use common notions and properties of circles and line segments as they are defined to prove the next result. And from this proposition on, we can now assume that we can move distances. And that will allow us to do a whole lot more things. Let's go back for a second to the propositions 1 through 5 because they set off a whole bunch of tools we will be able to use from now on. Proposition 3 says that for two given unequal straight lines to cut off from the greater, a straight line equal to the lesser. So again, thinking of measurements but not actually being able to measure, I would like to have an ability to move distances and their differences. Proposition 4, read it for a minute and see if you can tell in sort of modern language or description what this proposition actually is proving. If two triangles have two sides equal to two sides respectively and have the angles enclosed by the equal straight lines equal, then they will also have the base equal to the base, and the triangle will be equal to the triangle, and the remaining angles subtended by the equal sides will be equal to the corresponding remaining angles. Quite a mouthful, but if you draw the picture or just think a little bit more abstractly, you will notice that this is a familiar congruence property. I have two sides equal to two sides and an angle enclosed by them equal to. So if I have two triangles with side, angle, side being equal, then I'm guaranteeing the equality of the actual triangles. This is the side, angle, side property. Proposition 5 is talking about isosceles triangle and is going to actually heavily use proposition 4 in its proof. Let's next take a look at a couple of propositions and their proofs to really showcase how every subsequent proposition depends heavily on the previous ones. So Euclid is really building up this pyramid where some of the results are really basic and foundational, and as he keeps going, all of the follow-up results heavily rely on the previous ones. It is a very elegant and minimalist construction. He always needs something from before to prove something about where he's going.
For Book 1, proposition number 46 of Euclid's Elements, on a given straight line to describe a square. So with this proposition, we're given some line, in this case the line AB, and on it we need to construct a square. So to do this, let's first use Book 1, proposition number 11, which allows us to construct a line that's perpendicular to this line AB. So let's construct the line AC that's perpendicular to AB. So we can draw that here and label this C. And then next we'll use Book 1, proposition number 3, which essentially allows us to cut off a portion of this line AC equal to the line AB. And we can label this point up here, point D, so that the line AD is equal to the line AB. And now what we want to do is to use Book 1, proposition number 31, to construct a line parallel to the line AB through this point D. So let's build that line. And we also want to use the same proposition to construct a line parallel to the line AD through this point B. So let's draw that line as well. And we can label where these meet as point E. So first, we drew DE parallel to the line AB. Then using the same proposition, we drew the line BE parallel to the line AD. And now, since this four-sided shape we have is a parallelogram, because opposite sides are parallel to each other, we can use Book 1, proposition number 34, which says that in a parallelogram, the opposite sides and opposite angles are equal to each other. So we know that AD is equal to EB. So AD equals the line EB. And with this same proposition, we also know that the line AB is equal to the line DE. So let's write that AB is equal to DE due to Book 1, proposition number 34. And since AD and AB are equal, this implies that AB and EB are equal. So AB equals EB because of common notion number 1. Things which are equal to the same thing are equal to each other. And with that same logic, since AB and EB are equal, so AB is equal to EB, and AB is also equal to DE, then EB is equal to DE. So in essence, all four of these sides are equal to each other. So to show that this shape here, this four-sided shape, is a square, we just need to prove that all these angles are right angles. But we already know this angle here is a right angle since we constructed the line AC in such a way that makes this angle here right. So we also know, though, because of Book 1, proposition number 29, that if we have two parallel lines, the line DE and AB, and some transversal, this line AD here, then the two interior angles, this angle and this angle here, would have to add up to two right angles. So let's write that angle EDA plus angle DAB would equal two right angles. And due to common notion number 3, we can subtract off this angle DAB, since we know DAB is equal to one right angle. So subtracting it off would make the angle EDA equal to a right angle. So now all we have to do is use book 1, proposition number 34, which says that in a parallelogram, opposite sides and opposite angles are equal. So going back up to this parallelogram here, we just showed that this angle here is right. So now, because of this book 1 proposition number 34, the angles opposite those are equal, which means that they are right angles as well. So in this square, we have 4 right angles and 4 equal sides, which is exactly what we were trying to construct. So we can end with QEF.
Who knew that something as simple as constructing a square can be such a lengthy process? But try to do it with just a straight line, and you will find that this is actually quite difficult, because inevitably your angles are not going to work out. So somewhere in the middle of it are buried the facts that we have used circles and we've used our compass extensively. And again, going through all of these propositions, showing how the result that what you end up with is a square, you're working backwards through all of the propositions and the previous results and constructions that have been established. So this is kind of like wayfinding, knowing where you're going by knowing where you've been. Let's take a look at the last two propositions of book 1. The proposition 47 is what we know as the Pythagorean theorem. In a right angle triangle, the square of the side opposite the right angle is equal to the sum of the squares of the two sides containing the right angle. Whereas proposition 48, the very last one in book 1, is actually the converse of Pythagoras' theorem, stating that if I have the Pythagorean relationship that one side is the square of one side is the sum of the squares of two others, then what I actually have is in fact a right angle triangle. Let's take a look at how Euclid, not Pythagoras, actually proves it. So we will start with some triangle ABC. Now this does not have to be a right angle triangle, but what it does have to have is the relationship of the sides that we're after. So let's construct a little triangle here, and I'm going to construct it to be somewhat not quite right angle triangled, just to highlight the fact that I am trying to prove it's right angled, but I don't know that quite yet. So let's say this is A, B, and C. What I know though is I can have the relationship between the sides. So let's say BC squared is equal to AB squared plus AC squared. Excellent. What we're going to do now is actually construct something. We're going to first of all draw a perpendicular side to the side AC on the side on the left in my case of A, so that the length of my newly constructed side is actually equal to AB. Okay, so we're going to draw a line segment AD perpendicular to AC so that I have AD is equal to AB. Okay, so what I am constructing, I know for a fact, is going to be perpendicular. So bear with me here. Let's say this is approximately equal in length. And what I do know is that this angle by construction is actually a right angle. And this is the point I'm going to call D. Excellent. So what do I have now? Again, remember that my picture here is crooked on purpose so that we don't forget that we're needing to prove that that triangle is a right angle triangle, not given that it is. Now, let's use a cute little trick here. I am given that AD is equal to AB by construction. That's how I chose to construct it. And so that, of course, means that AD squared is equal to AB squared. And the cute little trick would be in using the common notion 2, I believe, that if two things are equal and I add the same thing to both of them, the result will be equal also. So what I'm going to add to both sides of this equation is actually AC squared, so that I eventually can use this expression. Okay, so I'm going to basically keep this as it were, and I'm going to add AC squared to both sides of this expression. By common notion 2, what I end up with, of course, is equality. However, what I have by this assumption is that the right-hand side here, AB squared plus AC squared, is the same as my assumption and therefore equal to BC squared. Let me create a little bit more room here for myself. So this is BC squared. Excellent. We're halfway there. What I also get from constructing this as a right-angled triangle is ability to use proposition 47. So what I'm going to do is actually connect the points D and C. And because I have constructed this as a right angle, my triangle DAC is in fact a right angle triangle. So I can utilize the Pythagorean property. Since triangle DAC is a right angle triangle, I know that the relationship between the sides holds. So since this is right angled, what I have is that DC squared is in fact equal to AD squared plus AC squared. And now let's look at what we have. We actually have a couple of things that are the same. Look, I have AD squared plus AC squared as the expression here. And I also have the exact same expression right here. So again, using one of the common notions, the transitory property, if this same quantity is equal to two different things, then those two things have to be equal to each other. So my conclusion here is that therefore I have that BC squared is equal to DC squared, which of course then implies that BC is equal to DC. Okay, let's maybe label this somehow on our diagram. Excellent. If these two sides are equal, what I can look at are the triangles DAC and CBA. Remember that by construction also, the two other sides are in fact equal. So this side is equal to this side, and fortunately they share this third side. So what I actually have is my left triangle over here is in each of its three sides equals to the right triangle over here. So what I have is, I can say thus, triangle DAC is equal to the triangle, keeping the same order. DAC would be BAC. If we are after a little bit more precision here, by the side property, which is one of the previous propositions, namely proposition 1.8. Now, as the very last step, if the two triangles are equal to each other via any property, all of their angles are also equal to each other. And specifically, this angle at A is equal to this angle at A. So the triangle inequality implies that the angle DAC is equal to the angle BAC. And of course, since DAC was 90-degree angle by construction, what this turns out to be is also 90-degree angle, and therefore our triangle CAB here is, of course, a right angle triangle. QED. Let's take a look at the last proposition of book 4, proposition number 16. This proposition is sort of a conclusion to the first 4 books that are books on development of the geometry of the lines and the circles. So it tells us to inscribe an equilateral and equiangular 15-angled figure in a given circle. So we are after an inscribed 15 gone. Now I'm going to do this construction by hand, so pardon some inaccuracies in my equilateral and equiangularness, but I just wanted to showcase the actual process as opposed to being exact and precise about it. We're of course going to start with a circle, and the first step, we're going to inscribe an equilateral triangle into the circle, which we can do as per one of the previous constructions. Again, remember, we are quite a ways into 4 books, so there are a lot of things we're now able to do. Here's an equilateral inscribed triangle. Next, we're going to inscribe an equilateral pentagon that shares a vertex with an already existing equilateral inscribed triangle. So let's say they're going to share this vertex, and I'm going to then construct a regular pentagon inside this circle that shares that vertex with my triangle. Okay, and here we go. Remember, I want 15 gone. So the trick here is to recognize that each arc that has this sort of pentagon edge, this pentagon arc here, in order for me to have 15 vertices altogether, each of these arcs will have to contain 3 vertices of my soon-to-be 15 gone. If this arc is to contain 3 vertices that are all equally spaced out, and I already have one, that means that this arc has to have one right in the middle. So I can bisect this arc, which is again something I know how to do, and find the placement for the new vertex of the 15 gone. And here I have my vertices that are equally spaced out within each pentagonal arc. Okay, so let's record this. I'm going to bisect this arc, place a vertex there, and now these are the spacings between the vertices of my 15 gone. And I can then continue to place them at the exact same length. Once I know how far apart they have to be, it's easy to place them around the circle. Okay, now again, of course, remember that my placing here is only going to be as accurate as my sketch has been to begin with, but this is not bad, right? Like even when I bisected this one arc to contain 3 vertices, I've noticed that these are actually pretty well spaced out. That is the construction. To wrap up this initial discussion of the elements, let's go back to the first 5 propositions. We noticed that in proposition 2, we use the construction of proposition 1, and same is true of proposition 3, but proposition 4 doesn't actually depend on 1, 2, or 3. So this could have been the very first proposition in the very first book. However, we must think that Euclid must have had some meaning for choosing this particular proposition to go very first, the very first thing that the reader encounters, constructing an equilateral triangle. And the meaning might become a little bit more clear if we think of what is the very last thing that Euclid proves in his 13 books. If he opens up with the construction of an equilateral triangle, what does he close with? Well, let's take a look at the elements. The easiest thing to do is to simply Google Euclid's elements, and you will likely, as one of your first hits, get this Clark University website that is the most comprehensive guide to Euclidean elements on the web. So if we go to the very last book, the very last propositions, here they are, actually highlighted in red, we notice that the propositions talk about the construction of a pyramid, the construction of octahedron, cube, icosahedron, dodecahedron. So the elements open up with construction of an equilateral triangle and close off with the construction of the 5 regular solids. There's like really beautiful symmetry in there to open up with the construction of the simplest regular figure and close with the constructions of the most complicated, in some sense, 3-dimensional regular figures. It's beautiful. This website contains a whole bunch of other really useful information. So if we scroll up to the top and pick a book, let's say we pick book number 1, once we get through the definitions and the postulates and whatnot, if we scroll all the way down, actually, maybe if we scroll all the way up and click on Guide to the book, it will give us logical structure of the book. This again highlights Euclidean genius of logically structuring propositions to really depend on each other, building up to the bigger results, building on top of something that will necessarily be needed in the propositions to come. Explore this website. I encourage you strongly to simply go to a book, click on some proposition, and see what the constructions are like. This follows Euclidean elements exactly, so you will get to see how the very first systematic approach to mathematics actually came to be. Euclid, in the exposition and its approach, is unique, and it is what we've inherited in the mathematical treatises today. So go back to the roots and explore the very beginnings of the formalism that we still use in mathematics.